lecture of this course EN203, and I am seeing quite drastic reduction in attendance just within 8 lectures. So what used to be 120, now it is at 68 including me, or 69 to say. So that's worrisome little bit. I don't know what's the reason. Sitting at home on Saturday doesn't make any difference. That's okay. Anyway, so let's start. So we are trying to discuss how to realize some of the basic gates practically, and there we have come across some of the circuits using the diode logic or resistance diode logic to say. So that portion we have completed. We have seen the shortcomings, we have seen the problems over there. So now we have moved to the next device, that is called BJT, and we have understood that this is a kind of control device, and more to emphasize on the control part, it is a current control device. So which means when we are injecting any current in the base, that is deciding how the device is going to behave. So basically 3 zones we have identified in the characteristic of BJT where it may operate depending on what is the current in the base. So we have seen that if we are not giving any current, then by default the device is in cutoff mode. So that is the first zone where the device operates. Then if we maintain the base current in such a manner that it's not very high and it is kind of following this relationship IC by beta, so this is where it operates in the linear zone or active zone, and which is where most of the amplifiers and all these things operate. Then third comes the saturation zone where we inject intentionally more than this IC by beta requirement. So this IC, I mean the maximum collector current what can flow through the circuit, through the BJT. So we are intentionally injecting more current than that, and what we are realizing that device actually stops following this previous relationship, or this equation is not valid. So in that case, we say that the device has gone into saturation mode, and the impact is the VCE voltage comes down to a saturation limit that is called VCE sat, and after that it cannot be reduced. So that is where it is operating in saturation zone. For our circuits, digital circuits, we use this first and third zones of operation. So either the device will be in cutoff zone or it will be in saturation zone in the steady state condition. There could be a transition when it is going from cutoff to saturation. In between, it may come in active zone for a short while, or vice versa when it is going. But that is allowed. So there is no problem in that. Only thing that we ignore this small overlap time period. That is called transition time sometimes. So we ignore that. We are not worried about it. Now we are trying to understand how these R1 and R2 can be decided so that we can force our device into saturation mode. So basically we are trying to decide the biasing for our circuit. So before going for that, we have seen that what basically this circuit will do, assuming that it is going into saturation mode and cutoff mode as per our wish. So we see that whenever we are giving any input voltage Vx at the base terminal connected through a resistor. So whenever this Vx voltage is high, what we see that this device voltage drops to VC sat, and when we keep in this configuration, this common emitter configuration, we will see that the output at this point Vz will be very small, 0.2 volts, which can be considered as logic 0 or logic low. So, and whenever we keep this Vx value low, that time the device will be in cutoff mode. So the voltage at Vz will be pulled up at VCC through this resistance R1. So it will be high or VCC. So that's the typical behavior what it will have. So it is kind of inverting the logic. Whatever logic we give at X, the output is having exactly opposite of that. So this is behaving like a NOT gate that we have seen. And when we are putting in this configuration, this is called the RTL, register transistor logic. So we are able to create NOT gate in this. We can create more gates using this RTL logic. But first we are trying to understand how do we keep our device in this saturation mode and cutoff mode at our wish. So basically deciding what are the values of R1 and R2 that can be chosen. So for that, first we have decided that what are the operating conditions, what are the operating voltages. So we have seen that for RTL logic, even for the other little bit advanced logic levels, TTL and CMOS, the VCC voltage is kept at 5 volts. And then the logic low for RTL is between 0 and 0.5. So why is it so? Because we have the base emitter diode which may break down after 0.6 or when we are keeping this voltage at 0.6. So we have to ensure that this junction is not forward biased whenever we are giving any voltage at this Vx if we want to keep the device in cutoff zone. So that is why we are restricting our maximum voltage up to 0.5 for the low logic. Am I clear up to this point? Now further, when we are deciding the high logic, we have to keep some margin between the highest value of low logic and the lowest value of high logic. So whenever some noise comes on that, still that should not affect your performance, the circuit performance. So we keep some 1.5 volts of noise margin, and our high level starts from 2 volts to 5 volts. Is it clear? So this is what the operating conditions are. Now with this, we are going to decide that what could be our R1 and R2. Am I clear? Yes or no?
Yes, sir.
Yes, sir.
Fine. So now we know that whenever this device is operating in saturation mode, then we have this relationship valid, VCC minus VC sat, because this voltage is fixed. It cannot be changed any further whenever the device goes into saturation mode. So the remaining voltage is getting dropped across this resistance R1. Clear, right? Now how do we choose? The question comes here. Or how do we start? Yes, any response? So how do we start choosing this R1 and R2? Yes?
R1 and R2. R1 can be high, sir, and R2 should be low.
Okay. R1 can be high and R2 can be low. This is your normal understanding is saying that okay, we want some more current over here, so R2 should be low. We want
Yes, sir.
this kind of relationship. Okay, this is one general understanding you may have. But however, no, we should have some more concrete evidence about what we want and how it should be designed. We should have some more basis of saying this, what value R1 can take and what value R2 can take. So let's start with very crude value. Let us say someone is starting with a very rough design and they are choosing this R1 as something like 1 ohm. Let's say there is no reason why they are choosing like this, but okay, let us say they are choosing 1 ohm. So what will happen if you choose a resistance like that? First, we should understand this thing. Let us say you have chosen 1 ohm. Now, what will be the current flowing in the transistor? Assuming that this is operating in saturation mode.
1.8 amperes. VCC minus VC.
So, which means the collector current flowing is almost like 4.8 ampere, isn't it?
Yes, sir.
Such a huge
Yes,
current,
sir.
isn't it? Now,
Yes, sir.
the impact of having such huge current, the power loss happening in this resistance and in the transistor as well, that will be huge. So for example, power loss in the resistance would be how much? 4.8 square into 1. How much this is? Quickly.
Sir, nearly 24.
So 23.04.
Nearly 23 watts. And what is the loss in the transistor?
Sir, loss can be
How much this is? 4.8.
0.96.
yes,
0.9.
0.96.
Still, the transistor loss, you may say that, okay, it's not very high, 0.96, but still, this is high compared to what the junction and all are going to see the temperature. That's not exposed to atmosphere. It is closed inside a casing and all. However, the power loss occurring across this resistance, that is huge, 23 watts. Typically, when we are choosing these resistors, these are called quarter watt resistors, which means what? Up to 250 milliwatt, any loss they can easily bear. But going anything beyond or close to this may actually spoil its characteristic or its value or its the whatever you want to say, the resistance value and the characteristic, how it's going to behave, everything may change. So definitely it's a too huge voltage, too huge loss for the resistance over here. So we cannot choose such a low value. Am I clear?
Yes, sir.
Am I clear? Yes or no?
Yes.
Now,
Yes, sir.
let us choose a very high value. Let us say one extreme is not good for us. Let's go to other extreme. Let us choose R1 is equal to 1 mega ohm. Now, what will happen? Yes, of course, the current will be very small, power loss will be very small. That's okay. But what is happening in the cutoff zone? When the device is in cutoff zone, what will happen? Now, we have understood that whenever any device is going into cutoff zone, it is like an open switch, isn't it? But this open switch actually we are saying relative to other components in the circuit. Other components means what resistance we are putting and all. But if the resistance value is so high, it is actually not an open switch, but it is like another high impedance. So you can say RQ is the cutoff zone.
Yes, sir.
Now this RQ cutoff, typical value could be like few hundred kilo. Okay, Tushar, can you mute yourself?
Yes, sir.
So this few hundred kilo ohm and this being 1 mega ohm. Now let us see what will happen when the device is in cutoff zone. So typically this voltage Vz, when the device is in cutoff zone, it should be what? VCC. That is the expected value, isn't it? Most of the drop should happen over here. Then only it will be pulled up to this VCC value. Now, in this case, let us see what is happening. If we have to compute Vz actual, what will happen? How much it will be? Isn't it?
Yes, sir.
Yes, sir.
Yes, sir.
Is it true or not?
Yes, sir.
Yes, sir.
Okay. So now, how much is this? 100 kilo ohm, or better to write in this manner. 0.1 mega ohm divided by 1.1 mega ohm. And this times of VCC. Now you can see this is roughly 0.1 VCC. So you are expecting 5 volts over here, whereas how much you will get over here? 0.5 volt. So this circuit is behaving in a different manner when you are putting very high value over here. So now we have to do some engineering. We have to come somewhere in between. We cannot choose the either extremes. We cannot go to very low value of resistance. We cannot go to very high value of resistance. Understanding my point? So, which is where we choose something which is incomparable to this. Like if this is few hundred kilo ohm or something like that, it should be smaller compared to this, but it should not be very small also. So a reasonable value, let us say, could be few kilo ohms. So let us choose, okay, 2 kilo ohm is our tentative value we choose for the design. Getting my point? Now what will happen?
Yes, sir.
What will happen to our IC? Let's say this is operating in saturation mode. So this is VCE sat. And here you are giving VCC. This is your R1, R2, Vx, Vz. Now, what is happening? What's the current flowing in this IC? Yes?
2.4 milliamp.
Am I clear?
Yes, sir.
Is this clear to all of you? Now, what is the power loss in resistance R1? Quickly compute. How much is this?
milliamp.
11.52.
Is this correct?
Yes.
Yes.
So now this is coming within our restriction of 250 milliwatt. That is the quarter watt what this resistance can accept. So this is a good reasonable design. Anything few kilo ohm could be good. You can choose 10 kilo ohm as well. So you need to compute corresponding to 10 kilo ohm what current you are getting. So this is fine. And obviously when this R1 is insignificant compared to this cutoff resistance of transistor, R1, Himanshi, can you mute yourself? Okay. So whenever this we are going to cutoff zone, our Vz will be all right. It will be very close to VCC because this R1 will be insignificant compared to this resistance offered by the transistor. And whenever we are in VC sat or the saturation mode, the current is also not very high. So this looks a reasonable design, isn't it? So we can fix the value of R1 that okay, we can choose 2 kilo ohm. This is fine. One resistance we have chosen, assuming that this is going into saturation mode. Now, the condition for sending it into the saturation mode is that we pump enough base current in the transistor. This is R1, 2 kilo ohm. How much is the current flowing in the saturation mode? 2.4 milliampere. So let's say the property of this transistor says that the beta value is 10. Transistor gain is 10. So what should be the base value minimum? What should be the base current minimum value?
by 9.
0.24 milliampere.
0.24 milliampere.
So I base should be at least greater than this IC by beta. It should be greater than this, isn't it? So which means I base should be greater than 0.24 milliampere. This is what we have to ensure at any cost so that this transistor can be taken into saturation mode whenever we apply the voltage Vx over here. Now another unknown factor is what is this voltage Vx? What we should assume? There is range because we are talking about saturation whenever this voltage is high, 2 to 5 volts. This is the range for high voltage. So what should be the Vx for which we can decide R2?
1 to 2.
Obviously, if we are able to pump this bare minimum current for the minimum value of the voltage available, then for any higher value, this condition will remain true. Yes or no?
Yes, sir.
Yes, sir.
Yes, sir.
So what we take Vx value as the high logic minimum value, 2 volts. And for this, we know that IB must be greater than 0.24 milliampere. So now, what should be our R2? So please also understand that whenever this is conducting, there is a drop of 0.6 volt corresponding to this base emitter diode junction over there. So this must be this Vx, whatever high minimum we are having, minus VBE divided by IB. So, or we should write the other way around. IB is related like this. And this must be greater than how much? 0.24 milliampere. So our R2 must be less than Vx minus VB divided by 0.24 milliampere, or 0.24 milli to say, so we can write kilo. Understanding my point? Now what are the values? What are the numbers? Vx is how much?
2.
2 volts.
2 minus
2 volts.
0.6 divided by 0.24. This is what is kilo ohm. Now what is this number?
5.83. 5.8.
So your resistance must be less than this number. Understanding my point? So generally when we are choosing the practical resistance value, we don't get all the values whatever we want. There are some discrete values. So something like 4.8 could be available, 5.6 could be available, 5.2 kilo ohm should be available. Now all these things will be available for the carbon resistors. Now any value, because all this come below this designated 5.83 kilo ohm value, so any value you can choose. Let us say not taking too less, because then otherwise it will pump lot of current. So across the resistor the loss could be very high. In the base emitter, that junction, the loss could be very high. So something like 5.2 or 5.6, no, this value you can choose. And if you want to have some margin, because these resistances may change their value, so you can choose 5.2 kilo ohm as the reasonably safe value for which your circuit will behave properly. Understanding my point? Now we have decided the parameters for this transistor when we are trying to bias it in saturation mode. Am I clear or not?
Yes, sir.
Yes,
Yes.
sir.
So it does not mean that you have only these two values of R1 and R2. For example, in lab we have taken 10 kilo ohm. So accordingly you can choose R2. You can compute, calculate back, and you can see that what value of R2 you are getting for this 10 kilo ohm. So here, as of now, we are choosing 2 kilo ohm, and we are getting something like 5.2 or 4.8 also could be okay sometimes. Vx, and here we are getting the Vz output. So this is what our common emitter NOT gate is. This is how it is realized. So if you have to plot the V input versus V output, or Vx versus Vz, so the graph may typically look like this. This small value is actually VC sat, and this is your VCC. So if we divide these zones, basically this is what we are saying, our input, this is Vx. So input is low, and that time we are getting the high logic at Vz. And this is where we are giving our Vx as high logic and we are getting a low output at VZ. In between, this is all undefined. This is where the transition is happening. So we are operating either in this zone or in this zone. This transition we are always ignoring. So we allow it, we give it sufficient time so that it settles down and then goes into this either the saturation mode or in the cutoff mode. Nothing in between. Am I clear? So this is what we are doing with RTL. We have realized the NOT gate. So with RTL we can realize some more gates. So let me check if something is remaining in this further. Then we will go to other logics. Okay, I think all the things are covered. Okay, fine. So we can go to realization of next gate using the RTL logic. So, and of course, no, here what we have realized is basically the NOT gate. That's all. You are familiar with this symbol, so I need not say much. Now let's go to realize the another set of gate. Let us see what happens. Let's see what we are getting. So you have a configuration something like two transistors connected or pulled up through the same common resistance, and the emitter is grounded. So it's very rare that we don't connect any resistance over here. Sometimes those configurations were also available. So generally it is not advised that you don't connect any base resistance. So Q1, and we can say this as Q2. So let's say inputs are A and B, and the output what we are getting is Z. So obviously when we are saying Z, the voltage is VZ, here the voltage is VB, here the voltage is VA. Understanding my point? Now, this is another configuration in which the transistors can be connected to realize another gate. Now what gate this is, we will see. So if you want to draw its equivalent circuit, you can take these transistors as switch. So equivalently you can draw it like just for your own understanding, for this simplification. The control signal is B over here and the control signal is A over here. Now this is what this is, right? Now what will happen whenever you give any input at A? When I say any input, which that means 1, otherwise it is 0. So whenever you give high logic at A, this will be connected, this will be turned on. And whenever you give any high logic at B, this will be connected. It is as simple as that, right? Now, let's say, even if one of the gates is connected, or even if one of the transistors are in conduction mode, what will happen to this voltage VZ or this logic at VZ?
Sir, low logic.
Yes.
Low logic.
Because any one connection over here will bring it down to 0 or we see set value, isn't it? So if you have to draw, or if you have to write the truth table, what it will be that if you give 0 0, which means both the inputs are not there, so what will happen to Z?
Sir, high.
High. 1.
So Z will be 1. And whenever you give any input, either 1 0 or 0 1 or 1 1, this output will be 0. Understanding my point? So which gate is this? Can you relate with any gate which you know?
No.
Nor.
Not it.
No.
No.
Is it?
Nor.
If you write the inverted Z of this logic, it will be 0 1 1 1. So your Z inverted is basically the OR gate. Or In other words, we say that what we have realized using this circuit is basically inverted NOR gate. Sorry, inverted OR gate, which is also called as NOR gate. Understanding my point? So we may have more inputs. Similarly, we can connect more number of transistors and we can realize all that. But we have to ensure that whenever we are taking this corrector current IC, or whichever transistor is conducting, or let's say all are conducting, we have to ensure that the base current is always crossing the limit IC by beta. So ensuring that condition, we may connect any number of transistors over here and we can have different inputs. So basically what we have done, that we have realized Z is equal to A plus P naught, isn't it? So symbolically we can represent this as the OR gate connected with a NOT gate. So this is what is our Z, and we can also say something like this. Clear? Now if you expand using our whatever principles we have learned, it can also be written as A naught dot B naught. So we can also represent the same logic in a manner where we have AND gate with both the inputs inverted. Understanding my point? This is not NAND gate.
Yes.
This is AND gate with inverted inputs. Now the NOR gate, what we have realized using this RTL logic, that is one of the universal gates. No, why universal? Because any other gate you can realize using this NOR gate. So that is how we say that these are universal gates. So these are one of the first gates which were realized using the RTL logic. It worked for some time, then people had to move for better logic design. Obviously, because there are so many constraints in this. We have to ensure that how much current is drawn, how much this base current we have to pump in and all that. So because of all these restrictions, slowly people started migrating to other logics. Understanding my point? But still it was, for some time it was used practically for realizing the gates and circuits. Am I clear? Yes or no?
Yes, sir.
Now once we have this NOR gate and the possibility for NOT gate, we can realize any other gate using this kind of configuration, using the RTL logic. Now let's move to our next logic design. That is called diode transistor logic. So basically whatever we have learned so far, we are only going to connect it together. It's called DTL. Another little popular compared to the earlier one, little more popular logic design, and here we had some better flexibility. So basically what we did, we combined whatever logic we had designed using the diode and whatever logic we have designed using the transistor. Getting my point? So let's say, for example, we have seen in the lab class also, this is our diode logic, and we have the inverter logic using the RTL or using the transistor. So basically what we do, we connect this output. So two options are there. One option was that we use something like this kind of configuration we use. Another configuration, what you have learned in lab, that you are connecting directly using a resistance. Similar to how we are having this NOT gate. You connect using this resistance. So these two options are there. Either you have these two diodes over here and then a high resistance, let us say some 20 kilo ohm or something connected over there, or you have some resistance similar to R1, R2 what we have designed. Now what is the difference between these? Both are correct, there is no problem in that. Okay. Now first let us see what is happening with this, what we are able to realize using this, and then we will go with the difference between the two. Okay, now as per our understanding, what is this gate up to this point? Let us say this point we call as some, okay, what to call as VC. Okay, VCC is already coming over there. So let me call as Vx. And then this as Vy, and then this as Vz. Okay. Now, as per your understanding, what would be the Vx, or let us say if I represent X. So what is this gate realized through the diode?
AND gate.
A into B. Now, when you move, let's say you are feeding this X to this transistor, it is getting inverted. So Z is basically, you can say that it is inverted X. So what we are realizing basically, Z is equal to the NOT of A and B. So this is what is called inverted AND logic. Why we are using these additional diodes, we will just see in a short while. So this is also called NAND gate. Am I clear? Now we can quickly write the truth table for this. So what will be the inputs and output? Can you tell quickly? So Z, and then we can have maybe X. We are not writing the intermediate thing. Okay. Now, can you quickly say what would be the inputs?
0, 0, 1.
Okay. What would be the outputs?
1, 1, 1, 0.
Isn't it? So which is what we have seen, the inverted AND. So whenever both the inputs are 1, it is 0. Otherwise, it is 1. That is the simple logic what it is following. So symbolically, if we have to represent, again, we can have something like AND gate connected to a NOT gate. Or we can club these two, or we can say this as another universal gate NAND. So this is also one gate with which you can realize any other possibility. So this is also called the universal gate. Now we may also represent this Z as A0 plus B0. So as OR gate with inverted NOTs. Any confusion up to this? This is what is our diode logic. Now let us see why we are connecting these additional diodes over there. Now a question. So what we have decided that the input voltage for this NOT gate or this common emitter voltage, what input voltage could be there for the logic low, the highest voltage?
6 volts, 0.5.
0.5. Why we are saying this? Because the diode may break down when we are going close to 0.6 or more than that, isn't it? So kind of we are restricted with 0 and 0.5 volt, this kind of input voltage. Now let us say we want to increase this margin because this is very small, only 0.5 volts. What we can do? So we can connect another additional diode over here. Now what will happen if you are giving input over here? What will happen? How much voltage now you need for breaking down these both the junctions?
1.2.
1.2. So isn't there some improvement when you are connecting a diode like this? Understanding my point? Now, why we are connecting two? Because in the diode logic, we have already one diode connected in this mode. So where it is giving the reverse drop. So one, we are compensating and then giving additional range for our low voltage. So 0.5, you can say it's 0 to 1 volt. So that way we are increasing our range for low logic. Are you understanding my point? So this is one way to connect your diode logic with the transistor logic and to say like the DTL.
Sir, can you please explain that compensation part?
Nothing. Let's say any voltage you are giving, it is getting reduced over here, right?
Oh, yes, yes.
That's all. So this is how this kind of, now here you need to give a pull down resistor, because if you are not giving anything, it has to come to 0. So you have to ensure that. So some high resistance could be there, 20 kilo ohm or 10 kilo ohm, whatever. So this you have to ensure that whenever there is low logic or something like that, it has to ensure that this is pulled down to 0. Clear? Any confusion? Yes or no?
Sir, can you repeat?
What?
The
entire-
use of 20 kilo ohm.
Yeah, here whenever you are giving any low logic, you are not sure what voltage is reaching over here, right? Because the barriers are not broken. There is no way to ensure the voltage at this point. Understanding my point? Unless the diode is conducting, you cannot ensure what voltage would be here.
Yes, sir.
Ashwin, fine?
Yes, sir.
So that is what we do. We connect a high impedance to ensure that whenever any reasonable voltage is not here, it is dictated by this ground. So we may have this pull up or pull down, these kind of configurations to ensure that if anything significant is not there, it is defined in this state. That is why you will hear the names like pull up or pull down, these kind of terms. Clear?
Yes, sir.
Yes, sir.
Now, so we have completed this DTL logic as well. So both the logic we have understood. Now here there is no difference. If let us say you want to go by this, whatever we are doing in lab, it's okay. Only thing you have to ensure that you cannot give more voltage over here than 0.5 volts. Or to say at this point, more than 0.5 should not reach. Otherwise, this will go into active zone. There is no other difference. You have only created another safety margin for your circuit. That is all you have done by using these additional diodes. Clear? So now from the experiment, actually I wanted to share something. Okay, so any problem are you facing in these circuits? First question is that. While doing experiments, are you facing any problem in this? So the basic difference from what is given in this circuit and what you are doing in Simulink is this device. We are not using BJT, but we are using another equivalent device which is voltage driven, that is called as IGBT. So only difference between this device and the BJT is that BJT is current driven device You have to give some enough current to maintain the biasing and all. That means the cutoff and saturation joule. Here, the same is ensured through voltage given at this terminal. You may connect some resistance, although it doesn't matter because we have in MATLAB a separate gate terminal given. So if this is how the block will look like, it is showing this terminal, it is showing this terminal, and here the gate signal is given. This terminal is not accessible. You are not connecting here anything. Just it is symbolically represented over there. But you are giving your signal over here. Understanding my point? These two power terminals are available for connection. That is fine. But this third terminal that is called again gate in this for this device it is called gate. For here you are calling it base. So anyway, so this terminal is not available or accessible for connection. So don't worry about it. You can give direct input over here in form of the pulse generator or anything. So anything, even if you keep 1 volt, this will turn on. But for keeping our understanding uniform for all the circuits, we will give input like 0 volt and 5 volt so that uniformity is maintained with our other circuits. Don't give anything in between. Understanding my point? Otherwise you will be confused. It is turning on for 2 volts or 1 volt. Yes, it will turn on. Don't worry about it. Because this is designed like that in MATLAB. There is no problem with the IGBT or any other thing. It is how it is modeled in MATLAB. Fine. Now let us say when you are connecting circuits like this or circuits like this, what you can do, you cannot have connection, no, because this is power terminal and here you are giving to signal. Power and signal cannot be connected. So always have some voltmeter measuring this terminal, and that signal you can feed to this. Some of you might be doing already like this, right? But in case you are getting confused how to do, I am just explaining this part. Any other confusion in these circuits while you are doing the lab?
No.
Basically, up to this point where we have done the DTL, up to this, these lab experiments are given. Yeah, tell. Someone was saying something. Any confusion up to this point? Clear, everyone?
Yes, sir.
Good. So basically what you have to do, you have to prepare this circuit or make this circuit, and then you feed the input such that you are able to generate all the possible combinations for the input. So let us say this is your pulse A which is getting generated. What you can do, you can shift your pulse B by some phase. No, so it could be something like this. So all the possibilities you can test over here. So for example, for this portion it will be 0, 0. For this portion it will be 1, 0. For this portion or 0, 1 to say because B is higher bit, let us say. Then this will be 1, 1. Then this will be 1, 0. So all 4 possibilities you will be able to test. Otherwise you need to stop the simulation every time, then change the logic, then check again. No, this kind of exercise don't do. When you are making, give it properly so that all possible inputs are generated automatically there. And so your all possible outputs. And need not run the simulation for 10 seconds or something like that. You can take sufficient frequency of this, let's say some 100 Hertz or more. So, and you can test this complete thing in, let us say 0.1 seconds or something. Am I clear?
Yes,
So
sir.
within few cycles you will be able to test all these things, but have sufficient time also, because these are physical devices. It may sometimes take time to go to one state from the present state. Okay, so have this margin also in mind. Although I have reduced the snubber effect by having higher values for the component and lower values for the capacitance. So still, sometimes it may have transient, though transient you need to ignore. You only need to look for the steady state values. For example, when these two are settled to a fixed value, only that input you need to consider. Clear? Fine. Any confusion up to this point? Yes or no?
No,
Okay.
sir.
No, sir.
Okay. So then we can stop the class over here and let's meet again on which day? Tuesday, I feel. Okay.
Thank you, sir.